So today what I'm going to do is go through the procedures that you'll be using for the developing working lab skills while preparing solutions. And as Pam will have introduced these solutions that you're preparing, 3 of the 4 solutions you're preparing, we're actually going to save and they'll be used in the analysis later on. The first solution that we're going to prepare is Part A, which is 250 mils of 0.1 normal HCl. That is going to be used in the mineral analysis lab, and because we need to make sure that there's no minerals in the glassware that we are using to prepare the solution, I'm going to introduce you to how we prepare the glassware first before we will make this solution. And then we'll make the solution using acid-washed glassware. That's the key, acid-washed glassware. So we're going to go to the back of the laboratory where the acid bath is, and I'll show it to you. Okay, so this is the acid bath. It's a 20% nitric acid. And what we do is we will soak any glassware that needs to be acid washed in a 20% nitric acid solution for 24 hours. And if Rachel can focus down inside here, you'll see a bunch of glassware. Okay, this is really dangerous stuff, and I have to wear special gloves. After they're taken out, they're rinsed with DI water using the DI process. We don't use any tap at this point, 3 times. And then we will rinse them with distilled deionized water. Distilled deionized water is typically the kind of water, I should say the purity of the water that we use in research labs and will be using in your teaching lab for any solutions. In order to prepare the 0.1 normal HCl, you will start by adding a little bit of water to this acid-washed glass. So these flasks were acid-washed overnight, then rinsed properly so they're mineral-free. A lot of times we'll use a volumetric to help us get solution we'll use a funnel to help get solution into the volumetric flask. So I'm going to do that. I'm going to just pour some water in here. Okay. And as you can see, this is distilled deionized water in an acid-washed glass. Okay. Then I'm going to take my flask over to the hood, and then in the hood I have the concentrated hydrochloric acid. I have a pipette that was acid washed that's going to be dedicated for using with the hydrochloric acid. Okay. You'll share it, so you'll use it and then put it back down on this saran wrap so that we don't ever want to put it somewhere else because it could pick up contaminants on the outside of the glassware that could then go into here. So what you're going to do then is pull this sash down a little bit. We're going to carefully pull up the proper amount of HCl that will go into here to create a 0.1 normal hydrochloric acid solution. I jumped from nitric acid to hydrochloric. So this is hydrochloric acid. Minerals are super soluble in hydrochloric acid or any other acid, and that's what we will use. I'm not going to do that. I'm just going to point out that you will then pull it up, and then based on your calculations, and then you'll dispense into the flask, okay, the proper amount. And when you dispense, you will have pulled up to 5 mils. This is a 5 mil pipette, and you'll dispense down to the proper volume needed. Okay. Anything that's left we're going to have you just dispense back into this bottle. Generally, you never return things to a stock bottle, but because I know that this has been acid washed and super clean, you can do that. So then anything that's left over, you will dispense back into here, touch the side, and then you'll lay the pipette down on that saran wrap. Put the cap back onto the bottle. Don't ever leave acid uncapped. Now you've got water with your acid in here. Then you'll take it back to your workstation. And at that point, you will then bring the volume to 250 mils. Okay? So I can pour as much as I can. We're just going to pretend that the acid is already in here. And if you run, and excuse me, because you're not at the meniscus, it's pretty hard. I have a transfer pipette for you to just keep on adding until the bottom of the meniscus is at the proper line. And then you're done. Okay? Put the cap back on the water, and you're done with this solution. You'll have parafilm that was on top of your solution. Put your thumb over it, and then we're just going to have you invert it a few times. And then you're going to return your solution to a storage container here. And it will get collected in this storage container. This is 0.1 normal hydrochloric acid, and so you'll just pour it into there. Okay? This glassware you then can take back to your bench and leave it. The next solution that you're going to learn how to prepare is a saturated solution. So the saturated solution that you're going to be preparing is a saturated sodium chloride solution, and we'll be using that for in the gas chromatography lab. It's part of the sample preparation. So to determine how much sodium chloride you would want to weigh out, it was recommended to look at something like the Merck index. And you are going to be making 50 mils, it says on step 3. So if this is actually a paper copy, a non-electronic copy of the Merck index, and you can look at it electronically also. And if I open the page to sodium chloride, and Rachel zoomed in, it says the density, that's what D stands for, is the density of a saturated aqueous solution of sodium chloride at 25 degrees Celsius is 1.202 grams. So you know that there can be 1.202 grams per mil, which means how many grams in the 50 mils. Well, I have done the calculations, and I have weighed out the amount of sodium chloride that you're going to need. So I'm going to just use a beaker that has a stir bar in it, and I'm going to put this whole bunch of sodium chloride in there. Then you should each have a flask that says water. This is general water. It's different than the water that's for the acid-washed solution preparation. And I'm going to measure out 50 mils because I want to make 50 mils. And again, if I can't quite pour it to 50 mils, I'm going to use a transfer pipette to add some more. So last week you learned about dispensing using volumetric pipettes for absolute accurate volumes. For the next type of tool that you could use would be a graduated cylinder. So there's pipettes and then there's graduated cylinders. And graduated cylinders can range anywhere from like 5 mils, I've even seen a 1 mil graduated cylinder, all the way up to 2 liters. This is a 50 mil one, and it's actually the next most accurate besides volumetric pipettes, not glass. So I'm going to add that into here, and you can see it's kind of cloudy, and a lot of times solutions are cloudy when you first make them up. That doesn't mean that it won't become clear, but if it's saturated and you have added a little more than what is needed, it will not clarify. So this is the stir plate with your sodium chloride in there, and I'm just going to turn it on, and there's a little magnetic stir bar that's inside of here, and it's spinning around, and we're just going to let it spin. When you're making up a solution in a beaker like this, you always want to label the glassware that you're working with. And so this is a good example of what you should not do. So what you want to do now, just to make sure, is just quickly, so in case this solution has to take a long time to go into solution, your chemicals take a long time, you want to say what's in there. So you want to say that sodium chloride in water. And then I can let it sit and work on something else, and I won't possibly forget what is in there because it's labeled. Okay. So I'm just going to stick this on there, and we're going to let it stir for a little bit to go into solution. Okay? And we'll get as much into solution as possible, but there should still be some salt crystals at the bottom, and when that is complete, you're instructed then we're going to collect your sodium chloride solutions in this bottle. This says saturated sodium chloride. This one's labeled in water. You always want to say what it's in, so you know it's not like in ethanol or something else. It has the class name 4312. And actually it has today's date, which was the date the solution was made. So when you're working in a lab, you always want detailed information on your glassware of what your solutions are. So the next solution that you're going to prepare is part C, and in that you'll be preparing first a stock solution of caffeine, and then you're going to learn how to prepare a series of dilutions that will then be used again for a lab in the future, and that will be when you analyze caffeine in different beverages by HPLC, high performance liquid chromatography. On your bench, you each have a vial that's labeled caffeine. That caffeine came from a stock container, and we just distributed it. We did that with the sodium chloride too, so that there would be a small amount in each batch for you to work with. So what you'll do is you'll take your caffeine, and you're going to take a little 10 ml beaker that tells you to use, and it tells you you're going to be preparing 25 mils, and so this is analytical, so we're using a volumetric flask for precise concentration. So you're going to prepare 25 mils of a 1 milligram per mil solution. Okay? And I know from, if you have 25 mils, that 1 milligram per mil concentration would be 25 milligrams in 25 mils. So to weigh that out, you need to use the analytical balance. And I always use glassine paper, and sometimes it has a little static electricity, and you have to break that, especially if you're wearing gloves. So you want to tear out the weight of your glassine paper, and you wait for your balance to stabilize, and then once it's stabilized, you zero it. And then I'm going to use one of these small spatulas to weigh out 25 milligrams. And I'm left-handed, so I'm working from the left-hand side, but if you're right-handed, you'd work from the right-hand side. And I am going to just take a little bit out. 25 milligrams is not very much. And what I have learned over the years of working in a lab is if I have a second spatula, which I've given each of you, I can kind of tap it in to get, I have a little more control of dispensing the amount of powder that I want. Okay? Sometimes it's hard to shake it off, so I'm at 16 milligrams, 0.016, 0.017 grams is 17 milligrams. So you're going to want 0.025 grams. So I need a little bit more. And so I'm going to just keep tapping until I get to my 25 milligrams. Now sometimes it takes a lot of patience to actually get to 25 milligrams. You tend to overshoot it or undershoot it. If you do that, it's okay as long as you know the exact concentration of your solution, your stock solution, then you can adjust your calculations based on that concentration. But we're going to try to get exactly 25. That would make us all happy and our lives a little easier. So it just needs like 0.8 milligrams more, which is like almost nothing. So I'm actually going to close the door a little bit on my hand for this, so I have a little, no air movement. And I'm just going to slowly tap until I can get up to my desired 25 milligrams. I think that the secret is tapping. I don't know if Rachel has her own technique, but...
I tap.
You tap?
Yeah.
Yeah, so she taps too. So we're all... It would be interesting to do a survey of people in research labs to see how they dispense very small amounts. If I were to dispense all of that, I know I would overshoot the market. So I just take a little bit at a time out until I get up to 25. Okay, I'm there.
Go.
Okay, so now I have gotten to my 25 milligrams, and I want to know what to do with this. I'm actually going to fold my paper in half so I don't lose anything. And then I'm going to take it over, and I'm actually going to use a beaker. So if you work in a research lab a lot, what you would probably do is put your powder directly into the volumetric flask, but it's a very small opening, and your chances of spilling it are really high. So we're going to use something with a wide opening, and we're going to just put it into a beaker. So we're going to turn it upside down, and we're going to just shake it until it all falls in there. And I look at the paper, and there's no powder left on it, and it's all at the bottom there. Okay, so we are back, and we have our powder, our caffeine in the 10 ml beaker, which was one of your supplies. And now I'm going to add some water into the 10 ml beaker to dissolve, to help it dissolve. So I'll dissolve it in the beaker, and then I'm going to transfer it into the volumetric. And you should have a little small stir bar that you can then put into the beaker and put it on your stir plate, and we'll stir it a little bit. And once that is dissolved, you won't see any little crystals of caffeine. It'll just be a clear solution. You'll transfer that into your volumetric flask. Okay, so my beaker, what I can see is that all the little crystals have dissolved in the water. So now what I'm doing is called quantitatively transferring. So I'm going to transfer everything that's in this beaker into the volumetric flask. Then I need to rinse the beaker 2 more times with water in order to transfer any residual solution that is in the beaker. Otherwise, I would probably have a lower concentration than I intend. When I'm going to transfer, I'm going to dedicate a transfer pipette that's only for transferring. So I don't want to mix this up with my pipette that I'm also using for water. That's a mistake that can be had, and if you do that, you'll contaminate the water, which is a problem. So rather than pour this solution. It's in the capping solution. I'm going to use transfer pipette and just put it in that way. Be careful to not knock your volumetric flask over. That seems to happen to people eventually. And then I'm just going to store this so I know I don't forget what it's for right there. Okay, so I don't use that for just pure water. Now I'm going to add some more water to my beaker, and I'm going to kind of rinse the sides. And I might even bring it over and I'll stir this one just a little bit to be sure and rinse it. Okay, this won't take much. And now I'm going to use the pipette that was being used for the capping already. Squirt that bit out, and then I'll transfer all this into here. And then I'll do that once more with the clean pipette. Use distilled water and rinse the beaker. It's kind of like when you wash dishes, and it would probably be most appropriate to rinse your beaker 3 times. Okay? And I'm going to transfer this in. And I'll get all of this in here. And then what I'm going to do at this point, I'll do one more rinse. Just do a little one and transfer that. And now I'm fairly certain that my beaker, any caffeine that was in the beaker is now in the volumetric flask. Okay, this is dirty, it's now considered trash. And we're done with that. So I'll use my clean transfer pipette to bring it to volume. And there's a meniscus. And you're going to actually be using these little volumetric flasks when you do the mineral lab again. But as you learned in the precision and accuracy lab, these are designed for containing an exact volume. So if you need to make up a standard, this was how you would do it. So I brought it to volume, and at this point what we're going to have you do is just shake it. We're going to shake it for probably about maybe a minute like this to shake it up, because the stir bar may not actually fit down the neck of the volumetric flask. After your capping stock solution is mixed up, you'll follow the instructions that are for your dilution of standards to prepare a series of microcentrifuge tubes at specific concentrations. So you will have calculated what goes into these cells, and the first one is a given example. Okay, so for the 0.05 milligrams per mil caffeine, I'm going to use 50 microliters of the stock solution and 950 microliters of water. Okay. You can't get a pipette tip down the neck of this stock solution. So what I'm going to do is use a clean transfer pipette, and I'm just going to reach down and grab some of that. It's even hard to get that. And I have a microcentrifuge tube labeled 1 milligram per mil, which is the concentration of my stock solution. So this is trash now. Okay, and I can put a cap on there. So now I'm ready. So it tells you for 0.05 milligrams per mil, you'll use 50 microliters of your stock solution. So you're going to use a pipette that some of you may not have used before. Each of your workstations has a sheet, and it has a sheet that describes the 3 different pipettes that we typically will use and how to set them to get a specific volume. So if you wanted 50 microliters, so you can see that says 50 microliters, you would choose the P200 pipette, and this is actually labeled P200, and it tells you to set it at 050. And if you look at the dial readings on this pipette, you'll see that there are no red numbers, meaning that there's no decimal points. So 100 actually means 100 microliters. So I need to dial this down to 50 really quick. So when I get to 50, there, okay, and now I'm going to put 50 microliters in here. I'm going to pre-wet the tip, and I'm going to depress to the first stop, which is the accurate volume. I'm going to pull up slowly my 50 microliters. Then I'm going to dispense it right back in there, blow it out. Okay, now I'm ready to get my exact 50 microliters. Depress to the first stop, pull up, wipe off the side, and then I'm going to dispense to the bottom the 50 microliters, pause, blow it out. Okay, so now I'm done with that. You can actually use the same pipette tip for all of your solutions for the standard because you're not changing the type of solution. If you were changing the type of solution, you would change your pipette tip, or if you were going down in concentration. Then it calls for 950 microliters of water. So you'll use your 1 ml pipette tip, 1,000 microliters, set at 0.95, the 0 is red, so that's 950 microliters. And then I can just use my distilled deionized water, pre-wet the tip, dispense back, take my accurate volume, which is the first stop, and I'm going to dispense into 1 microcentrifuge tube. Okay, I'm going to cap it, and then you'll need to vortex it, and I don't have a vortexer here, but it'll be in your bench. It just is a way to spin it around and mix it. It's a special device called a vortexer, and we'll show you that. Okay? So you'll do that for all 4 of these standards, and then you'll have your stock solution, and then we will collect those standards for analysis by HPLC. And unless you have any questions, that is it for making the caffeine standard. So the last solution that you're going to prepare is a buffer solution. And remember, a buffer, it has both a weak acid and weak base, and they're designed to maintain a pH of a certain solution. So they resist a pH change. You're going to be making up a acetate buffer. It's called it's a sodium acetate buffer, and you will have you're actually given all the information on how to make up the acid and base solution, and then you will have calculated how much of the acid and how much of the base that you will then use to mix together to get pretty close to the desired pH that you want. Okay. So the acid solution is the 200 millimolar acetic acid solution, and that is actually prepared from glacial acetic acid, and you'll make that up in a volumetric flask, so it's at its exact volume again. And I have this labeled 200 millimolar acetic acid, and it tells you to use 2.8 mils of acetic acid, and then you're going to bring it to volume with water. Okay, so acetic acid is also known as glacial acetic acid, and that is located in the graph here. Okay? And this is it, glacial acetic acid. And this is not acid, this has nothing to do with acid-free or mineral-free, so we don't have to worry about like we did with the HCl. So I have a pipette that's dedicated for the glacial acetic acid, and so you'll just follow the instructions, and we can take this volumetric out, or this funnel out, and you'll take up the 2.86 mils of glacial acetic acid. I think I'm going to do that so that we can mix the two together and then measure the pH. So I'm going to bring my acid up to 5 mils. I'm hoping my bowl works. Do I have a bowl that doesn't work? Nope, it works. Okay, so I'm at the bottom of the meniscus, and it called for 2.86 mils. So I'm going to be careful, try not to drip this, and I'm going to then dispense down to 2.86. And I actually put a little black mark with Sharpie on this glass pipette so that you would know where it's at. Sometimes it's hard when you've got a partial unit to know where to stop. Okay, so I'm there. So what's left here again, I'm going to actually put back into this bottle and dispense the rest back. And then I'm going to actually blow out the last bit, catch the side. And you can just lay the pipette down on the absorbent paper, put the cap on the acid bottle, and now you're ready to bring this to volume. Okay, and I can kind of swirl it around to help it mix. And then I'm going to bring it to volume with some more water. And as I approach the set mark, I always stop, and then I use a clean transfer pipette, and then I'll use a transfer pipette to bring it to volume, as opposed to trying to pour it, because chances are you'll over pour. Okay, so I have now an exact concentration of 200 millimolar acetic acid, and I'm actually going to put parafilm on top of this and then dispense it shake it many times, or else we'll have a ground glass stopper for them. So you can mix it up really well. And then I'm going to make up the next solution, which is the 200 millimolar sodium acetate solution. That's step 3. And it actually tells you how many grams to weigh out. It says 4.1 grams of sodium acetate, which I have done here. Okay, so now the question is how do you transfer it from there to here? So there's a couple possibilities. You can try to just tap it in like this. It has a little point, and you can probably do that if you're careful. Or you can use your funnel as an assistance. And you can add a little bit of water to this to rinse the last little bit out. Now, if you're not comfortable pouring from the whey boat into here your solution, what you would do is you would put your crystals into the funnel, and then you would slowly add water to bring them into solution, to get them to dissolve and go through. We'll leave that up to you to decide. For the small volumetric, it's pretty hard to get it in there, but I think for the larger one, you should be able to. Okay, so I need a little bit more again. If you get low on water, you can actually walk over and refill. It'll look differently upstairs, but this is distilled deionized water, and you can just refill your flask. Don't use the DI water from the tap, from the sink. Use the water from the bottle that water comes out, it's the same as what comes out of the deionized faucet, but it's been through a distillation process too. So we tend to use only that kind of water for our research lab, and I think Kim's lab does that too. A little bit more. Okay, so now that is, I can clearly see that there's crystals at the bottom of this, so you are going to need to put a stir bar in there to get it into solution. Your volume is set, so when you add put your stir bar in there, it'll actually look like you have more volume than your 250, but that's okay. Okay. So where we're at now is you will have finished preparing the acetic acid and the sodium acetate. And then based on your calculations, using the equation, you will then use a certain volume of each of those, mix them together, and the goal will be to reach a solution that has a pH of 4.15. And I'm going to, you can see I've got my beaker here, acetate buffer, pH 4.15. So I've measured out 2 solutions and of the volume that I know we need, based on my calculations, and I'm going to just mix them together in this beaker. Okay. And then I'm going to put them on the stir plate so that they behave themselves and mix well. And now I should, if everything was done correctly, be pretty close to 4.15 pH with my acetate buffer. You're going to use a pH meter to confirm that, and what I'm going to do here is just teach you how to calibrate the pH meter, and then you can use it. If your solution is off in pH in the end, I'm not going to show you this part, you'll use a 0.2 normal HCl solution, or 2 normal HCl or a 2 normal sodium hydroxide solution to bring the pH to 4.15. The reason we chose 2 normal is because it's quite a bit more concentrated than your 200 millimolar. You always want to choose an acid-base solution for adjusting that it has quite a bit higher concentration, otherwise it will require too much volume. To calibrate the pH meter, you'll take off, so the electrode is stored in what's called electrode storage solution, and this just unscrews, and you can leave the cap and the little O-ring in there, and it'll actually slide up if you're careful. Okay, and you always want to rinse off your electrode before you put it into anything. You'll use a squirt bottle of deionized water to rinse the electrode really well. And then I stick it in there and get the bulb rinsed off too. And then, sorry Rachel, after you're done rinsing it off, you want to take a Kim wipe and you want to just blot off the water. You don't ever want to rub it, you just want to blot the water off. You can actually scratch the membrane of the little glass electrode, okay? So, are you ready? Okay. So this is one example of a pH meter. There's several different kinds of pH meters up in the teaching lab, and we will assist you if you need to on how to calibrate it, but we want you to understand that you need to calibrate a pH meter before you're going to use it. If somebody else has already calibrated it that day, then you generally don't have to calibrate it, but you're going to be the first person to use it, so we're going to calibrate. So you do this by pressing, actually what I'm going to do is just turn the instrument off. Okay, so down here is the on-off button. I'm going to press that to start with, and it pulls up some stuff, and then eventually it'll tell me that it's in the measure mode up here, but I want it to be in the calibrate mode, so I'm going to press the calibrate button, and now it's flashing calibrate. And once it gets a stable electronic reading that this solution is 4.01, it'll stop. It won't stop flashing, but it'll say ready over there. Then I'll press enter, and then I'll take the electrode out, wash it off. Okay, there we go. So it just said ready. It said ready, then it went away. Sometimes that happens. It'll be ready, and then you want to just lock it when it says ready. Okay, we're ready. So now we're ready. So now you can see it's flashing on the pH. So it's telling it that it's now, ready for the next standard. So we rinse off the electrode before we put it into the next standard solution. Very well. Take a Kim wipe to blot off the water. That was really smooth.
Good catch.
Good catch. Yeah, and I have a pH 7 standard, so you always want to calibrate your pH meter so that it brackets the pH of the solution you've just prepared. So we want our pH of our solution to be 4.15, so we want to use a pH 4 and a pH 7 standard. If your solution had a desired pH of, say, 8, you would use a pH 7 standard and a pH 10 buffer standard. So now it's flashing to identify, and it's ready now. Okay. So now I can go back out to get to ready to measure. So now I'm in the measure mode, and so I can now then rinse off my electrode, and I'm ready to measure the pH of my solution and then adjust it if needed. So this electrode is on an arm. Some of the pH meters in the teaching labs don't have arms, and you'll have to just put it in there. So you'll stick the electrode in, and if it was correct, it should read 4.15. This says 3.9. So I've overshot with the acid. So I want to add some base. I would add the 2 normal sodium hydroxide base to bring it up to 4.15. And so that's it for the procedures today. You learned how to make an acid, a mineral-free acid solution, a saturated solution, standards for analysis, and then a buffer. So those are 4 pretty classic types of solutions that are made in research labs, and if you do work in a lab, you'll have lots of opportunity in the future to use these.